Hello, everyone. This is Professor Rahal. This recording is for class on Monday, tomorrow, 0206. And in this recording, I'm going to go over the solution to the class exercise compute distances, which was given to you as a zip folder with a write-up. We'll go over that, and I'll need to highlight a few things related to Python and Thani. But first, we'll start with the Raptor portion. If you recall, you were given this Raptor program over here. It's almost complete. It asks the user to enter 2 points, the coordinates for them, x1, y1, x2, y2, sets the distances to zeros, and then displays the 2 points as well as the computed distances. And as you recall, from the write-up, the formulas are given to you over here. So for the most part, what we had to do was we needed to replace these two assignment statements with actual formulas based on the write-up. So to compute the Manhattan distance, we had to get the absolute value of the difference between x2 and x1, and then add to that the absolute value of the difference along the y. So y2 minus y1. That would be for Manhattan. And for the Euclidean distance, it's similar but slightly more complicated. It's the difference along the x's again. So x2 minus x1, okay, raised to the power 2. So that would be square plus y2 minus y1, also squared, and we want to square root the whole thing. There are a few options we could do. We could either raise to the power half, 0.5, that will do the trick, or you could use a built-in function called SQRT that allows us to compute the square root of a certain value. So it doesn't matter which one of the two you use, as long as you get it done. Now, now that the program is ready, I will run it, and we'll look at the test cases over here. So the first test case, x1, y1 is 1, 1. 1, and then the second point would be 7, 7. And as we see over here, the Manhattan distance was 12 as expected. Let's see what happened to the output. And the Euclidean distance is 8.4853, which is exactly as shown in the table. Let's try the other points. We've got now 0, 0, 1, 1. I'm getting 2 and 1.442 again. So you could try it for all the rest, and you should get all the answers to match exactly as shown. And then we talked about that in class, that the most important thing here is to thoroughly test your program so that to make sure it works for every case, not for 1 or 2 cases only. Now, this exercise, now that it's done, we could go ahead and launch Thani and write the corresponding program in Python. So here is that. It's good to have samples with you, just in case, so that you don't have to remember the exact syntax all the time. But I'm going to call this, let's save it I'm going to save it on my desktop. I'm going to call it compute distances. Yeah, so this is that. And we're going to go through the program one line at a time. The Raptor one, and translate it into Thani. So starting with the first one, we have variable x1 that will contain the value entered by the user, who will see the prompt enter x coordinate for first point. So in this case, x1 would be an input, okay, with the prompt enter the coordinate for the first point, the x coordinate. And because what we're expecting to get from the user is a number, we have to convert whatever input it is to a number. So this is converted to an integer, assuming it's an integer. If not, we can use float. Same thing for the second input, which is the y coordinate for the first point. And then we'll repeat these two for the second point. So x2, y2, and then that will be x2 will be the x coordinate for the second point, and y2 would be the y coordinate for the second point. Okay, so far my program will allow me to enter 4 different values. It's not going to do much other than that, but at least I know that much is correct. Next, we have to do the computations. So I'm just going to copy what I've written here to Thani and see what needs to change. You know, sometimes you don't really have to change anything. Other times you'll have to change. So Euclidean distance as a variable would be the square root of, I've got x2 minus x1 raised to the power 2 plus y2 minus y1 raised to the power 2. And then the whole thing needs to be the square root of that. Now, if you run that 1177, it's going to fail because it's going to tell me a function square root doesn't exist. So in Raptor, it exists, but in Thani, it does not exist. There are a couple of ways around that. You could either, again, do what we said before. You could raise this whole thing to the power half, in which case 1177, okay, we'll compute a value, and then you can see the values over here, which I've forgotten to show the variables. So I do that, view variables, and as you can see, it actually computed the correct Euclidean distance over here, 84 and 8.4885, if I'm not mistaken. That was the expected answer. Yep. So that's that would have been fine. Another alternative would be in Python, there are some libraries that you can import, which will give you access to additional functionalities. So we can say import math at the top. Not that we have to put it at the top, but math is a library that contains a lot of built-in functions. So now once I import math, I could say math.square root. Okay. And then close that here. That should work now. 1177. Okay, and it computed the Euclidean distance as we expected over here. Manhattan distance is similar, but the name, of course, is going to be Manhattan. So I'm going to copy it here to here so that I don't make a typo, and then simplify it to use absolute. So ABS of x2 minus x1 plus ABS of y2 minus y1. And ABS is a valid function in Python, so you could use it with no issues. You're probably wondering, how do you know if a function is available or not? Typically, you're not expected to, but with practice, you'll get to know what are the standard functions that are always available, like input and int and absolute, and what functions require you to import certain libraries. But for now, the basic ones, ABS is basically available. And then finally, I have to do 4 display statements now to display the output as shown here. So I'm going to copy this first one down to print. And we'll do, this is the first print statement. I put it exactly as is without any changes. I'm gonna do this, not you. I'm gonna do the second one also here. So again, print the second one. Print the third print statement. And then finally, the fourth one. Yeah, so all I did was I just copy pasted from Raptor. And you could tell now that the process really is this. We already solved the problem in Raptor. What we're doing here in Python or Thani, we're just rewriting it in a different way, basically. So now my program should start producing output and displaying it as we expect, 1177. I must have missed something here. Yeah, I probably need spaces in here, and I need to fix the output also, because I cannot use plus with numbers and strings, so I convert these to strings. And again, this isn't the best way to do it, but for now I'm just copy pasting from Raptor, and I'm just going to do the minimal amount of work to get the program to display. We'll do it in a better way shortly. 1177. So now it gave me the correct numbers. The Manhattan distance is 12, and the Euclidean distance is 8.53. Now here, you are asked to display things limited to 3 decimal digits, so rounded to 3 decimal digits. So in this case, we're going to have to use a different print statement than these. So I'm going to start changing them to use the advanced string formatting that basically looks much better than the way we've done it. So we'll get rid of all of these here, and we'll just put our strings. So the first one is going to be a D, that's x1, comma D, also D, right? For the second one, the Y coordinate, that would be dot format, x1, y1. Okay, so one line at a time. I want to see if I've done it correctly. So I'm going to run the program again. Okay, so it is displaying correctly. Now I can change that one to print the second point, x2, y2, x2, y2, and then I will, so these we've already done, and then these two I'll copy down here and fix. So now we need the distances displayed to 3 decimal places only. So that would be F for floating point number, and I need it to be 3 decimal places. So 0.3 or just 0.3F would do the trick. And now I can get rid of the annoying string functions and the plus character, and then use the dot format. I believe this is correct now, but only one way to tell. 7, 7, and now it's basically displaying them as expected. We can try another test case. Let's do the -1, -2, -3, -4. We should get 4 and 2.82 something. -1, -2, -3, and -4, and then we're still getting the correct answers. Now the challenge problem at the end asks you, can you do all of these in a single print statement? And the answer is, the only reason I have separate print statements here is because I want them to appear on separate lines. But you could tell Python to do that on the same line by using the \n character. Whenever Python sees that in a statement, it interprets that as start a new line. So if I were to put it, for example, over here, yeah, /n over here. So I took the first one and put a /n. Notice how the output is going to change from this line to this line. 7, 7. So notice this first time when I tried it on line 9, this is what I got. But then when I attempted it with the \n, this is what I got. So I can use the fact that I know that every time Python sees /n starts a new line to put everything together and then separate them by new line. So that would be /n over here, and then I'll do the next line over here, /n. Now it's probably going to need to make it a bit larger, and then get this line over here, /n, and start a new line, And then finally, this line over here, put it at the end. So that would be, this is the first line, the second line, the third line over here. See, without the extra spaces. And we also now need to update the variables. So this would be the first and the second one over here. This one now should be x2, y2. Just for clarity, I'm going to take it to the next line. X2, y2 over here, and then we have Manhattan, and then we have Euclidean. Yeah, so now in the same print statement, x1 is going to display here, y1 here, x2 here, y2 here, Euclidean Manhattan distance here, and Euclidean distance here. So 1, 1, 7, 7. There you go. And that should be all for this recording. Thank you much for listening so far.